Right, hello everyone. So this is what we're going to do today. Is I just want to have a look at some of the results that were on the cluster. That's the first thing I'm going to do. Have a look at those results. The second thing I'm going to do is I'm really going to try and position us for the real task of the course, which is molecular docking. So I want us to start using Autodoc tools to get us in preparation, get us all prepared for the molecular docking side of things. I want you to have a look at the, I need you to have a look at the RCSB to find some structures, to download some structures, because that's going to be really important. And that'll also position you for getting a nice write-up together that just remind you that it's due by next Friday. So I hope that you're recording and you're getting all the data and you're writing exactly what you do in your write-up so that I can see certainly from the write-up that you're able to do all of the tasks that I've set in you. Okay, so what I want to do first of all is I want to go into the cluster and just to have a look at my results. And so if I can just go to Putty, I'm going to go to, so my apologies if my terminal doesn't quite look the same as yours. That's because I've broken my terminal. Don't worry about it. And I just haven't bothered to fix it. But your terminal will look much better than mine in terms of telling you exactly where you are on the system. Okay. So normally what I do is before I do anything else is I do this module add to make sure that I've got access to Gaussian. What you might like to do, so I do module add Gaussian Geo9 EO1, and I'm using the right click to paste, works nicely. And then often what I'll also do is I'll module add XTB in case I'm going to be using XTB in the session. So if I forget to do that, when I come to try and use Gaussian, it'll complain. If I come to try and use XTB, it'll complain, and then I'll remember and I'll put it in. So it's not a transmission, and I'll put it in immediately. But I want to look at what I did yesterday. And remember yesterday I told you about this little checkpoint file that we could create. And here it is. I've got 5REY ligand.chk. That contains a lot of information about orbitals. So it's extremely useful to create it. And it's just a little bit of effort to get it to show orbitals. So it'd be nice to take it and open it in Avogadro and see if we can see the molecular orbitals for that particular ligand that we ran yesterday. Well, there's just one thing we need to do with it. We need to change it to a formatted checkpoint file. So the way we change it to a formatted checkpoint file is we must make sure we've added the module for Gaussian, because this is a Gaussian command, is we do form check. And you'll see how this works is that this checkpoint file, if you try and open this checkpoint file in a Notepad++, for instance, it is a huge mess of things. But if we can create a formatted checkpoint file, then you end up with a file that you can open a Notepad and you can actually read. So I'm going to type form check, and I have to type exactly the name of the checkpoint file. So there it is. Here it is. So here, so you type exactly form check and the name.chk of that. And when you do that, notice that it'll just tell you what the output is. The output is 5rey.fchk. So this is a formatted checkpoint file. And what is interesting is that this original checkpoint file is only for the version of Gaussian that we've got. So it's a particular checkpoint file that's understood by Gaussian 09. The formatted checkpoint file is a format that is understood by everyone, not only by Gaussian and Gaussian software and Gauss View, etc., but also by other softwares such as VMD, such as Avogadro that we can have a look at now. Okay, so that is really important. That's your final thing. Okay, so now I need to copy it to my local computer, WinSCP. When I copy it to my local computer, it's carbon. I could save this, but I'm not saving it to in case people have missed things. So if people have missed things, then if I don't save, I'm not taking shortcuts, and you can see me doing it the way that works perfectly every time. Okay. And so here we go. I'll find, where's the log file, 5REY. There's the log file. I need that log file. And I need that formatted checkpoint file that I created, the 5REY log and 5REY ligand. You must copy both across. And you'll remember in the past, we opened the log in Avogadro. I'm going to do that now. I'll open the log in Avogadro. So here's Avogadro. Let's open that log file. It's 5RE, it's a text log, 5REI ligand. Now what's nice about Avogadro is that if I open the log file, it also checks to see if there is a formatted checkpoint file with it. So it's really important that the formatted checkpoint file is with it. So we're not opening the formatted checkpoint file, I'm opening the log, but Avogadro will know. It will know that the formatted checkpoint file is there. And when you open it, you can tell that Avogadro has found that formatted checkpoint file because you can see these orbitals over here. So you can see all of these orbitals, and you go down, it's got all of these orbitals. I don't know if I can make this a little bit, let's make it bigger, and hopefully I can see, because I don't want LUMO plus, there we go, there's the highest occupied molecular orbital over there. And so when you click on it, you can then see there's your highest occupied molecular orbital. And we can maybe just go, and there is your lowest unoccupied molecular orbital. Okay, so that is fantastic. That Avogadro has automatically picked up that the formatted checkpoint file is there, and so it gives the orbitals. But of course, the calculation I did yesterday was not just opt, it was not just optimization, it was opt-freq. There was frequency as well, which means that vibrational spectra results are available. And you see on the right, you can just, it's picked up. There's vibrational spectra available. It's good practice to check there are no negative frequencies, there are no imaginary frequencies, or else you need to, you've got a problem if there are. But now you can show your spectra. And here's my simulated infrared spectra. Okay. So there we can not only get orbital information in Avogadro, but you can get your infrared spectra in Avogadro. So what would be nice is that before you continue, maybe you write up, just show me or place in your write up that you know how to get some of the properties of your molecules. For example, molecular orbitals, and for example, spectra such as the vibrational spectra. Okay. If you want to try and predict NMR spectra, just drop me an email. I'll tell you what changes you need to make, or you can look on the Gaussian website and go through it, and you'll see what changes you need to make in order to predict other spectra, for instance, NMR. Okay. So that there is how you can get nice properties from QM calculations. You can visualize them using Avogadro, but of course, we've got to have the formatted checkpoint file to do so. Are there any questions before I continue? Because I want to move on to molecular docking now. Okay, right. Now, it doesn't matter. It doesn't matter whether you've used XTB to optimize your compounds or if you've used Gaussian to do them. I'd like you to be able to use both. But of course, if you're in a project, I really advise you to be consistent. If you're preparing high quality ligands, please, and you've got a lot of them to work with, stick with XTB for it. Or if you've got a few, stick with Gaussian for it. Don't mix and match. Just keep consistency in whatever project you're doing. So for example, in this project, I'm interested in using XTB, but of course, the XTB was run on 5-REC ligand. There's 5-REC ligand .xyz. Remember, that's what I ran. I did XTB, 5-REC ligand, and I did minus ops. Okay, and it went through, did the calculation. Okay, and of course, it produced this output here, xtbopt.xyz. So what I want to do, so let's see if I ls, if you do an ls, you can see there it is. There's the XTB opt that we got there. But for molecular docking, I really want that to be in PDB format. And of course, it hasn't got the right name. It should be 5-REC ligand. So I'm going to sort that, or something with to do with 5-REC. So what I'm going to do now is I'm going to just use Babel. So the input is an XYZ format, and it's xtbopt.xyz, and the output is PDB. And I'm going to do 5-REC, and I'm going to call it lig. Hang on, I've mistyped 5-REC. And I'm just going to remind myself it's from xtb.pdb. Call it like that. So we put it like that. Okay. And so it's converted and it's created 5-rec ligand xtb.pdb. Okay. So please, this is a very good point to just alert you to a problem that can happen when you're working on the cluster. And the problem is, what if I put spaces in the name of this? What if I'd had called this ligand 5-rec space ligand space xtb.pdb? You'd see that if I had spaces in the name, can you see that I'm no longer typing 5 words on this line? If I put spaces in the name, you've got 1 word, 2 words, 3 words, 4 words, 5, 6, 7 words in that line. And so it's this Babel command here is not going to work the way you want it to. So please, can I advise you never to put spaces in a name. If you want a space in the name, rather use the underscore like what I've got here. Okay. The important thing here is I have optimized with XTB and I've got the molecule in PDB format that is ready now for use in molecular docking. So if we go to WinSCP, I don't see it here because I need to just quickly refresh. And there it is. There's the ligand. I can copy it to my local computer. Okay. So now we are ready to use that ligand for molecular docking. Okay. Any questions so far? Right. What I want to do at some point is to create a flow chart, just to remind you of a procedure we've gone through to get to this point. And so we can make a nice flow chart. Now, maybe we'll start it at the end if I've got time. Okay. Right, so I'm going to close. I don't need the cluster anymore at this point. And I don't need a terminal putty at this point. I'm just going to kill it. Okay, and so what I hope that you had installed was Autodoc Tools. And when you start Autodoc Tools, it'll take a moment to start, but it'll look something like this. Okay. The first thing I want you to do when you come to Autodoc Tools is please, first thing, set the working directory. Set it to the directory where all your systems are, where all your molecules are. So it's File, Preferences, and Set. You've got to go to File, Preferences, Set. If you do this, it's going to make your life a whole lot easier, because then Autodoc Tools will know where to find everything. And if you don't do this, you'll find that some of the docking won't work, because when it runs the docking, it doesn't know which directory to find everything in. So you set. Okay. So problem is, here we go. This directory is probably not quite the right one. So let's okay. We need to change this. And if you, we could type documents, but what I found is that if you just make sure, if you make a change here and make it wrong, if you put something wrong in here, and you try and set this to be something wrong, it'll come up with an error message, but it'll at least give you a way to browse for the directory you want. Okay, so I've given it a wrong directory. What I want is to find my documents folder, because that's where everything is at the moment. So there's my documents folder, and I'm going to set that. So it's got C users, documents, and I'm going to set that. And so now when I run, it's going to look for files that are in that directory. And when I save files, all files are going to go to that directory. And so as long as I stay working in that directory, there's going to be no conflicts of not being able to find things. So please always set the directory. It's a bit finicky to get the directory set, but please make sure you can set it. Right. Now, to deal with the ligand, the small ligand that we are going to attach, that we are going to try and fit inside the protein, to deal with the ligand, we need to use this bottom set of tools here. We need to use the ligand menu here. And I'm just going to go from top to bottom. The input, I can't choose a ligand because there's no ligand open in my workspace, but I can open a ligand. So please go to the ligand and you go input and you can open a ligand. And it's not showing me anything because I want PDB files. You've got to change this to look for PDB files. And when you change the PDB files, you'll see there's my XDB created ligand that I've used, be able to put in PDB format. So please, you need to tell it to look for PDB files the first time you run this. The second time you run it, you'll be fine. You will have created a PDBQT file format, which will be fine. Now you can open it. Okay, this is interesting that when you open it, it said it's added gastric charges. It's merged 10 nonpolar hydrogens. That's very important to note. It's detected 4 rotatable bonds. Okay, so that is, all that information is really, really important. You might want to record some of it. But it's interesting, it's merged 10 nonpolar hydrogens. So when you have a look at your molecule, you can see that this is a particular case where not all atoms are shown. And in the docking calculation, these hydrogens are inconsequential to the docking process. And so the CH is a united atom. Our CH is at that point, it's just represented as a single carbon there. Okay. But of course, the hydrogens that will be involved in hydrogen bonding are consequential. And so those are shown. So remember, to get to this point, we did ligand input and we opened. Okay, right. What's interesting now is you don't have to go into the other menus. Input's really important, and we want to save it. And the output, I'm going to save it as a PDBQT. I'd like to look at one of the other menus and just go save directly. But the other menus are quite interesting because you can have a look at the torsion tree, and you can show that's the basis for it. Just hang on, just try some of these. If you go to choose torsions, that's really nice. The choose torsions shows in greens those 4 torsions. That bond here is said to be rotatable. That bond said to be rotatable. That bond said to be rotatable, and this 4th bond is said to be rotatable. So in the docking process, it's going to rotate about all 4 of those bonds to try and find conformations. Okay, the red bonds are not rotatable. You can imagine if you tried rotating about that bond, you would break the ring. And it's picked that up, and it's determined that you can't rotate there. And of course, that OH, if you try to rotate there, it doesn't change the position of that. But of course, we're not going to make any changes here. Okay. So what that does, the important things here is you input, you open, and make sure you open a PDB type, and your output, you save it as a PDBQT file type. Okay. If I ever come back to this ligand again, of course, I don't have to create a PDBQT because it's already been done. I could simply reopen the PDBQT. But of course, in that PDBQT, it has that information on those 4 rotatable bonds for that molecule. So this PDBQT is all set for this conformational search within the context of molecular docking. Okay. Queries. So your task will be on the cluster to either take your log file to PDB or your XDB file to PDB. Copy it back to your local machine and see, can you use Autodock tools to set up the ligand for docking. Okay. Can I just, if I've got a bit of time, can I just go to PowerPoint and can we just try and see where we've started and where we've come to. So if we start, notice that we started with Marvin sketch, didn't we? Okay, and of course, don't forget there's detail within Marvin sketch. So for example, we did conformational searching, or we did search for tautomers. You can do all of that, okay? But that's important. I think we can full detail in on that. But really, what we did is either we save as Gaussian.com file. If we saved it as a Gaussian.com file, that gives us one way of working things. Another way we worked with is if we saved it as XYZ, for example, that gives us another way of working with things. So from Marvin sketch, we could go either one of those 2 ways. Of course, if we saved it as a conf file, we needed to do a little bit of extra work. We needed to go to Notepad. Okay, we needed to use Notepad++ to add the %mem, %check, and %inproc shared. Okay, with XYZ we didn't have to do that, but of course with both of them we had to use WinSCP to copy to the cluster. So both of them, once you've got the conf file, you have to copy to the cluster. Okay. After copying to the cluster, the next stage was putty. Okay. And with putty, once you're in with putty, once you're connected to the server, there were several other things that we had to do. Of course, we have to either module add. We did the module add. That must be a small m. This autocorrect is driving me mad. Module add Gaussian G09 Gaussian. And it was, if I got this wrong, remind me. We've got 10 minutes left. That's enough time to, just from here, just remind me, Gaussian G09.EO1 is correct, yes. So we could either go that route, or we could do module add XTB. It's very important in this case if we don't have capital letters. So we could do either of those. Okay. And of course, if you go the XTB route, what you do is you would have to then type XTB molecule.xyz. You'll change it to whatever molecule it's supposed to be, and minus opt. And that then produces the output we had. Okay. If you went the Gaussian route, remember we did, we had to do a lot of things. We had to do qstat to check what was going on. We have to do sub G09 batch, autocorrect, sub G09 batch molecule 8 and qstat again, just to check what's going on. Okay. And if with XTB, what we did straight away, we could get the open Babel, the XTB opt. We can use Babel minus I XYZ, the XTB opt. That's created .xyz. And then we can do an output PDB, the molecule opt.pdb. So we could easily get that back to PDB format. With Gaussian, there's several things we can do. We could use Babel to create a PDB file. We could do Babel minus input is G09 molecule.log minus O PDB molecule opt.pdb. Okay, so we can easily create optimized PDB from that. But of course, what was nice with Gaussian is if we used WinSCP, we could do, remember the form check? We could do the form check of the we do the form check of a molecule. Then, of course, what we can do is then we copy the log and FCHK file back using WinSCP. Okay. Then open the log in Avogadro. And what we got is molecular orbitals. And of course, if we did opt and freak in the calculation, then of course, then we get the IR spectra. Okay. Okay, does that give you an idea of where we've gone to? I think I've missed out a lot. So I haven't gone into detail of the conformational searching in terms of Marvin's sketch. I haven't gone into details of exactly the changes we made at the top, but you can look back to see what they are. I haven't put in details of where we've connected, but does that give you an idea? What I haven't done as well is what do we do with these PDBs? These PDBs these PDBs can be opened in Autodoc tools. There's not space to say copy using WinSCP, but I'll just say WinSCP and then so Autodoc tools. Okay, and maybe we need a totally different slide to how we deal with Autodoc tools. Okay. Any questions?
Yes, Prof.
Yeah.
So with Marvin sketch,
Yes.
if you draw your molecule and then you do the conformer search and you find that you drew the wrong conformer, can you then take the right conformer and use that going forward, or do you have to redraw it in Marvin sketch?
No, in Marvin sketch, the conformational search. If you've drawn the wrong conformer in Marvin sketch, you can easily, you can run a long conformational search. You will find the right. It's more problematic if you've got the wrong stereochemistry. If you've got the wrong stereochemistry, then you in problem. I'm just going to open one of these. So here we go. Here is so for a conformational search. So if your stereochemistry is wrong, then you need to redraw. You need to make sure, change a bond to get the right stereochemistry. I think you need to go back and be careful about it. But if you've got the right stereochemistry, then in terms of conformation, you can't really have a wrong conformer. You just go to your conformational search and you ask it to return only the lowest and make it a bit of a longer search. Make the search longer, give it 90 seconds, click some of them, and just go okay, and give it a long time, and I'll very, very, very carefully search for the right conformation. And I trust me, that conformation you get in the end will be much better than your starting conformation if there's a problem. Does that answer the question?
Yes, okay. Then when I get my right conformer, can
Yes.
I then use that one to do my calculations?
Yes, yes. Rather use the right conformation for your calculations. Use the lowest energy conformation for your calculations. Okay. Any other questions? I know this Zoom session is about to die. We've got 2 minutes remaining. 2 minutes. Time for one more question? Okay, so I want you to get as far as molecules in Autodoc tools. So you need to have at least one molecule fully set up for molecular docking by tomorrow. And please look ahead. There's some files that we need from RCSB. So look at the handout I have. Please look at those files from RCSB. There's some links. The protein structures are the other side of what we need. Have a look at those. If you download those ahead of time, it'll save you time tomorrow, because that's the other side of what we need to do, is we need to get those proteins. Okay. Right. Okay. So I think we've run out of time for questions. So if you've got more questions, please email me. Okay. And I'll be happy to correspond by email. Please be patient. It might take half an hour sometimes for me to respond to an email, but I will respond. Okay.